Yesterday, we reviewed logarithms. That wasn't the exciting part of yesterday. The exciting part of yesterday was introducing this new number that has a lot to do with exponential functions and logarithmic functions, the number e. And, I claimed, I suppose, that it's one of the five most important numbers in all of mathematics. Again, it depends on the branch of mathematics that you're working in, I'm sure, but it's a pretty big deal for us. I think it's safe to say. And you're going to see why today. We're going to start doing derivatives. Today, we're only doing derivatives of exponential functions and expressions. And then tomorrow, we're going to be doing derivatives of logarithmic functions. Then we're going to start using those derivatives to do things like sketching and that kind of stuff. Um, and the sketching is really cool. There's different things about it, which is really neat. And there's a lot of really different graphs, different from anything we've ever seen. I think it's really cool. We're going to do a cool activity as well to really get you thinking and connecting with this stuff. But anyway, that's in a few days, something to look forward to. For now, we're going to just look at the basic derivatives. But the other thing I said yesterday about exponents, so the number e has a big impact or is really relevant in exponential growth. So things like interest on money, that sort of thing. And I said that. But once you see how it's useful in derivatives and in calculus, I think you'd be surprised that it wasn't calculus where this number was um, discovered or not invented, but became popular and was used. It wasn't early on. I think Leibniz was one of the early users of this number, and Leibniz is famous for inventing calculus. So yeah, I'm sure that it was early on in when people discovered this number that it was used in calculus. But I would have thought that it sort of grew out of calculus, but it didn't. Okay, so um, let's start with let's start looking at the derivatives of this stuff. Okay, so we are going to look at f at x equals b to the x. Whoops, to the x, where b is greater than 0. If b, was one of the conditions that we talked about. If b is negative or 0, then exponential, it wouldn't be a function. Exponential functions, it doesn't make sense for the base to be negative, right? So we're considering any base b. And from first principles, what do we mean by that? We mean we're going to try to figure out what the derivative is. So remember in Unit 2, when we first started talking about derivatives, in fact, in Unit 1, we talked about the definition of the derivative using limits. And then in Unit 2, we started looking at derivatives of different things. And a lot of it we built from first principles. So we're going to do the same kind of thing here. It's a little bit different for some you'll see when we get there. There's some things about this that will be a little bit different. But anyway, so if f at x is b to the x, some base b, any base, then its derivative f prime is the limit as h approaches 0. Now you're starting to remember what I meant by first principles of f at x plus h minus f at x over h. Okay, but what is f at x? F at x is b to the x. So this is equal to the limit as h approaches 0 of b to the x plus h minus b to the x all over h, which equals the limit as h. Well, hold on. Before I go any further, what do you think we can do with this? We have to start manipulating this in order to simplify it to something that I suppose we know what to do with it, to rewrite in another way. So what can you possibly think of to do? There's not a lot to do, but there is one thing. Maybe you thought of it. B to the x plus h is the same as b to the x times b to the h. Why? Well, x squared times x cubed is x to the 2 plus 3 which would be x to the 5, but that's not what we care about right now. It's that 2 plus 3 part. So what I've done is I've gone the other direction. I had a sum, so I went the other direction and turned it into a product of two exponential expressions. Well, now what can I do? Now I can common factor out b to the x. This is b to the h minus 1 over h. Okay. Now what can we do? Well, there's two ways that we could approach this. I'll briefly go over both, but I think the one that is most convincing, who remembers this? Remember this from when we did all of those proofs? And what I'm going to do is I'm going to use limit property 5. Okay. And by limit property 5, this is going to be the limit as h approaches 0 of b to the x times the limit as h approaches 0 of b to the h minus 1 over h. So by limit property 5. Number 5. Again, these are not universal numbers. This is just the sheet that we use. Okay, so by this limit property 5. Okay, now here's the trick. This doesn't have an h in it. So the limit as h approaches 0 of b to the x. B to the x is actually a constant in terms of h. Now this is something that maybe some people wouldn't quite understand, because b to the x changes as x changes, but b to the x doesn't change as h changes, right? No matter what h is, b to the x will always be the same, because it only depends on x. B is a given base, so b is not really changing. It's for any specific base that stays the same in this case. So x would be changing because as the function value changes, or the location of the function changes. But when we're doing this limit, it says h is changing. So b to the x is a constant in terms of h. So I could have actually used limit property number 3 as long as we understand that b to the x is constant in terms of h. But that's why I like limit property 5 a little bit better, because instead I break it up into two separate functions. But one of them now I can see, well, it doesn't have an h in it. So this is just equal to b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Okay, so now what can we do? We've gotten it this far. If you think back to when we did other derivatives from first principles like this, we were able to rewrite the entire thing in terms of something that we could recognize. So who recognizes this limit? Anybody? Probably not, because it's not one we've ever seen. And in fact, the proof of this is beyond the scope of this course. It's too hard for us. So all I can say is turns out that the limit as h approaches 0 of b to the h minus 1 over h is equal to the ln of b. So a specific case of that would be the limit as h approaches 0 of 2 to the h minus 1 over h would equal the ln of 2. Now, I have tried and tried and tried to come up with a good way of us trying to figure this out on our own, but there really just isn't one. I would still basically have to walk us through the entire thing. Yes, I could convince you by showing a bunch of values and showing that it's approaching the ln of 2. So like what we would do is we would do ln of 2 oh, it's 0.69314711806, and we could do a bunch of stuff to show that we're kind of approaching that number, but that's not a very obvious number to approach. It's not like I'm approaching 3 or approaching 0. So I never felt very good about that. I've made up an applet in GeoGebra to try to demonstrate it. Even it's not very good. It's still, to me, not much different than me just telling you what is the case here. So it turns out that this is the case, that this limit is the ln of b, which means the derivative is b to the x times ln of b. So if f at x equals b to the x, where b is greater than 0, then f prime, its derivative, is equal to b to the x times the ln of b. And that's the derivative of any exponential function. Okay? Box. But hold on, there's more. What if the ln of b was some easy number like 1? What if ln of b was 1? I want you to think about this for a second. Go back and think about what we just did. We're looking at the derivative of some exponential function. So it might be f at x is 2 to the x, or the function is 10 to the x, 3 to the x, 4 to the x, whatever, right? We're finding the derivative of that function. So this would be g prime is 10 to the x times ln of 10, right? That's what we found. Interesting that it still has that same 10 to the x in it. So what if ln of b was 1? Well, why am I saying this? Because if the ln of b was 1, this part would go away. Well, what does it mean for the ln of b to be 1? This is log base e. Base stays the same when the base is e. Something unbelievable just happened here. If you haven't seen it yet, that's okay. Okay? But I want you to see if you can observe or figure out for yourself what that means, because its implication is pretty astounding. Okay, what it's saying is if f at x equals e to the x, then f prime is equal to e to the x times ln of e, which equals e to the x times 1, so just e to the x. So that's saying that its derivative is itself. It doesn't change at all when you take its derivative. And this is what I was saying before, in that it's amazing that the number e didn't grow out of calculus. Remember, sometimes when we're using logarithms, we get to choose the base. And if I'm doing calculus, and I'm taking the log of anything else, I'm taking the derivative of any other base, I'm going to end up with this annoying little constant that happens. So if p at x is 2 to the x, oh, I did 10 to the x above, that's right, but I'll do this again. Then p prime x is 2 to the x times ln of 2, and we already saw that ln of 2 is about 0.69 something. So it's a constant. This is just a number, but it can be really annoying to have to write that every single time and include that in my calculations. So man, is it ever incredible that when I am, if I get to choose the base, I would choose e if I'm taking the derivative, and that constant is gone. And it's just amazing that the derivative of e to the x is e to the x. Isn't that unbelievable? And that's why it seems almost like this was invented for calculus, but it's not where it was discovered, but it does happen to be the case. So the other implication of this, and this is interesting, is something that people will describe and comes up here or there. Now, how useful it exactly is for us in our unit, probably not very much. But what it also means is, which is, like I say, just kind of interesting, if I have a graph of y equals e to the x, then its derivative is also e to the x, and the derivative is the expression for the slope of the tangent. So if I pick a point and I do the tangent at that point, if that point is at 3, then the slope of the tangent is 3, right? Because it's the same function, so you're subbing in the same x value, so you're going to get the same output. And if it's a derivative, that's the slope of the tangent. If it's the original function, then it's just the y value, right? So kind of interesting. At any rate, I'm going to summarize this for what we're starting with, because we're going to start doing derivatives of exponential functions that have base e. And so remember this notation. Uh, Derivative of e to the x is e to the x. There's another way that we sometimes write this, d by dx of e to the u, where u is some other function, right, is equal to e to the u times u prime. So if we have some other kind of function in the exponent, we can't get away with it being that simple. It's not always going to be the easiest derivative you're ever going to take. You thought taking the derivative of sine was easy because it's cosine. There can't be an easier derivative than e to the x because its derivative is itself. But um, of course, it's going to be a little bit harder than that. Otherwise, we'd kind of be done the unit, I suppose. The derivative of logarithms is a little bit trickier, but it's also quite simple, maybe unsurprisingly. Okay, so this is where we're going to start with some derivatives with base e. Here we go. So for this first one, y equals e to the 3x. That means my u from the last page that we just talked about would be 3x, which means u prime is obviously going to be 3. So y prime in this case is e to the 3x times 3, right? But of course, we would write that as 3 e to the 3x and do that in one step once we get better at this. Okay, so let's do a few more. In this case, my u is 5x squared, so y prime is going to be negative 7e to the 5x squared times the derivative of the exponent, 10x, or simplifying, negative 70x e to the 5x squared. Some cool stuff starts to happen when we take derivatives and second derivatives of these, and when we do more sketching, we're going to see that happening. And because I end up with the original function in the derivative, if I take the derivative again, I'm taking the derivative of that as well as the derivative of the rest of it, kind of thing. And so you get this kind of repetition happening over and over again, which is neat. Okay, what's happening in this one? Hopefully we recognize that this is the product. It's a product of two functions, so we have to use product rule. Okay, so f prime is the derivative of the first thing, 2x, times the second thing, plus derivative of the second thing, which is e to the x squared, okay, times the derivative of the exponent, which is 2x. So that is the derivative of the second thing times the first thing, which is x squared. And in fact, take a look right there. Even when we're not taking the second derivative, there's a cool thing that happens when we're doing product rule, where I end up with the function, the exact function in both parts of that sum. And now I can factor that out. I also have a 2x that I can factor out of both. That was just because this part happened to be the same as the exponent. That won't happen every time. Okay, so I am going to simplify this first. 2x e to the x squared plus 2x cubed e to the x squared. So I can factor out a 2x e to the x squared times 1 plus x squared. Okay, and if I was solving, setting this equal to 0 and solving, then of course that's exactly what I would be doing, factoring it like that so that I could solve it. In fact, I've got three products because I've got 2x e to the x squared and then 1 plus x squared as well. Okay, let's keep trying some more. This one that's my exponent. So be careful that you're reading that correctly. So this is e to the 6x squared minus 5x plus 4 times the derivative of the exponent, which is just 12x minus 5. That ones like that aren't going to come up very often, but again, it makes us just focus on what we're doing and on these special rules. Okay, dy by dx equals, I'm just using that to change up the notation. There's no real reason behind that. E to the root x. What is the derivative of root x? 1/2 x to the negative 1/2. Okay, because don't forget e to the root, or the square root of x is x to the 1/2, right? So when I take its derivative, I bring the 1/2 out front, subtract 1. So that ends up being e to the root x over 2 root x. Hopefully that's familiar. We did a lot of that back when we first started taking derivatives. So I hope that that kind of thing, derivatives of square roots, is still sort of fresh and not too easy for us. Okay. This is implicit differentiation, isn't it? So we're going to, I don't know what our instructions were. Instructions were not find dy by dx, so that doesn't really make a whole lot of sense. It says differentiate, but this is what we're going to do. We're going to find dy by dx when I take its derivative. So derivative of the left side is dy by dx. Derivative of the right side, that's not a product. 5 times e to the xy is not a product because 5 isn't a separate function. So this is just 5e to the xy. But when I multiply by the derivative of the exponent is product rule. So it's x times y. Derivative of x is 1. So 1 times y is y, plus x, the first thing, times the derivative of the second thing, dy by dx. Expanding my bracket, times y. Or I could have written that, I suppose, would be a little bit better, as 5y e to the xy. And then 5 plus 5x e to the xy dy by dx. Okay, moving all the dy by dx's to the same side. 5x e to the xy dy by dx equals 5y e to the xy. Factoring dy by dx out. Whoops, 5x times e to the xy equals 5y e to the xy. And then one more step, dy by dx equals 5y e to the xy over 1 minus 5x e to the xy. And I think that's as far as we can take it. Okay, so implicit differentiation, like always, requires a little bit of extra carefulness. In this case, there was a product in our exponent. Okay, let's see, one more, then we're going to try something different. And this is the derivative with respect to t, because it's f at t, functions in terms of t. And that means this is quotient rule. Okay, so f prime at t is the derivative of the top. So the derivative of the top is a sum. Derivative of 1 is just 0. So the derivative of that 4e to the 3t is 4e to the 3t times the derivative of the exponent, which is 3. Okay, actually, I'm going to do that in a different color so we can see it. So this is the derivative of the top times the bottom minus derivative of the bottom, e to the root t times 1/2 t to the negative 1 over, sorry, 1 over 2, yep, times the top over the bottom squared. E to the 2 root t, okay? Um, there's probably possibly some stuff in there, yeah, that I could factor on top. I'm not going to. We would clean that up because this has fractions and fractions, but I'm not going to worry about that right now. Questions like that are probably not going to be too common in what we're doing, but watch for quotient rule, watch for product rule, all of that same stuff that we've done before, okay? All right, try something else. Find the equation of the tangent line to the function f at x equals e to the 1 over 1 minus x. So this is a little bit strange because that's the exponent there, okay? Be careful of that. On a quiz or a test, if this came up, we'd be careful. Probably should have brackets to be a bit more clear. So let's find the equation of the tangent line. How do we find, what do we need for the equation? We need the slope and we need a point. Well, we've got the point because it gives us a point, not just the x value. So all I need to find is the slope. How do I find the slope? With the derivative. So let's go ahead and take the derivative. Oh, actually, before I do that, I'm going to point something out because this is going to make our life a lot easier. Isn't this e to the 1 minus x to the negative 1? It is, because it's 1 over 1 minus x. So this is going to make our life a little bit easier writing it like that. Always be looking for those little tricks that help with efficiency and help, make not just efficiency like in terms of quickness, but make it your life easier, right? So e to the 1 minus x to the negative 1 times the derivative of the exponent, which is bringing the negative 1 down, times 1 minus x, subtract 1 from the exponent, negative 2, and then we'll be very careful, times the derivative of what's inside, which is negative 1, because the derivative of negative x is negative 1. That would definitely be something that people would miss. So be very, very careful with all of these. The same things back from when we did derivatives of polynomials at the very beginning always apply. Be very careful for derivatives of what is inside things and just take it nice and slow every step at a time. Same as trig. With trig, you're looking at exponent, trig, angle, right? You're really like slowing yourself down to remind yourself of those rules. The same thing is going to apply here. Yes, this part doesn't change, but when you're doing the derivative of the rest of it, you got to be very careful. Okay, I'm going to clean this up a little bit. It's going to make it easier to punch into my calculator. This is e to the 1 over 1 minus x, so I just rewrote that back the way it was before, over, okay, the 1's cancel, so negative 1 times negative 1 is just positive 1. And then this becomes 1 minus x to the positive 2, okay? And I want to find that at 0. So that becomes e to the 1 over 1 minus 0 over 1 minus 0 squared. Okay, and that is e to the 1 over 1. 1 minus 0 is 1. So e to the 1 over 1 is e over 1 minus 0 is 1. 1 squared is 1, so e over 1, which is e. If you need to do that a little bit more slowly and evaluate some of those things, go for it. Trust me, that is what it works out to. It works out to e. Often we try to set these up so it kind of works out to something that's not crazy, but of course there are no guarantees. Now, for the equation, we are going to use our trusty old formula, y minus y1 equals m times x minus x1 at the given point, 0 and e, and where m, our slope, is equal to e. So y minus e, that's our y1, equals e times x minus 0, which works out to y minus e equals ex. So ex minus y plus e equals 0. And it looks kind of weird, but e is a number, so that's like 2x minus y plus 2 equals 0. Standard form again, and that one worked out fairly nicely. Okay, so that is doing some derivatives, using derivatives a little bit of exponential functions when the base is e. And that is lovely because the derivative of e to the x is e to the x. It is itself, which is fantastic. But we have one more thing left to do, and we've got lots of time, so that's great. And the last thing that we have to do is, what if our base is something other than e? So we're going to do a little bit of work with that and see what that looks like. And it's going to be important that you practice both of these because this will come up once in a while. It's something that you're going to be tested on for sure. So if f of x is b to the x, and b does not equal 1, because if it's 1, then we don't have a very interesting exponential function, okay? But it's not, it works mathematically, it's just not interesting. And then b is also greater than 0. This is the situation that we're looking at. We're actually going to sort of rederive something that we already know, kind of circular, but it's interesting, so we're going to go ahead and do it. Okay, first thing I am going to do, and this is a little bit tricky, but if you remember this property, I can do 7 to the log base 7 of anything. So let's say n will equal n. So I can use this backwards, where if I start with n, I can rewrite it like that. So my n in this case is going to be b to the x, and I'm going to rewrite f at x as e to the ln, which is like 7 to the log base 7 of b to the x. All I've done is use one of these properties of logs and exponents to rewrite this, but I know that this is something that people can't follow really clearly or really quickly. Like, I get that. So you can either trust me, take my word for it, this is true. It is something that we've talked about, that we've done. If you're not convinced, come back to it after and convince yourself that this is true. Again, it's just a property. It's just using that property of logarithms. Okay, now I am going to do a little bit of work in the exponent. So this is equal to e ln of b to the x is also x ln of b, right? E to the x times e to the x times ln b. So that's that property that brings the x out of the exponent. Okay, so this is the f at x that now I'm going to take the derivative of. So it's e to the x ln b times the derivative of the exponent. Well, ln b is a constant. B is the base, so if it's 2 or 3 or 4 or something like that. So ln of b is a constant. So this is like the derivative of 2x, which is just 2. So this is ln of b. Okay, that looks like I was supposed to be taking the derivative of ln of b, but I didn't. I took the derivative of a constant times x, which is just equal to that constant, right? Well, e to the x times ln of b is equal to b to the x. So now I can say this is equal to b to the x times ln of b. Now, when we first came up with the derivative of e to the x and saw that it was e to the x, right? The derivative of e to the x is itself. We did that by using the special case of this, and then I used e to the x to rederive something particular. Kind of weird, but anyway, this is very similar to some of the other proofs that we did with log properties, so it's kind of neat. But what we did was we refigured out what the derivative of a function is of any other base, right? So I'm going to write this out again: d by dx of b to the x equals b to the x times ln of b. That's where B is any base, could be E as well, but generally speaking, we're talking about other bases. And then d by dx of b to the u, where u is some other function, is equal to b to the u times ln b times u prime. Okay, so a lot of what we're going to do is we're going to be doing derivatives of things with a base of e. That's primarily what we're going to do, but every once in a while this is going to come back up, and like I say, it's going to be on the test, so you just can't forget that you just got to add in that ln of p. You got to add that little constant in, okay? Please don't forget that. Okay, let's take a look at a couple of examples here. Y equals 4 to the x squared. Y prime is 4 to the x squared times ln of 4. This is the part that we were skipping when we were doing e to the x, because it'd be ln of e, and ln of e is just 1, so we were skipping it every time, times the derivative of the exponent. Okay, so it's as easy as that. It's very similar. What if this was y equals e to the x squared? Then y prime would be e to the x squared times the derivative 2x. And like I said, it would be times ln of e, but that's just 1. So we ignore it. Okay? So be careful when you have a base of anything other than e that you remember that extra constant. We'll do a couple more of these. Y prime equals, this sure looks like product rule. Derivative of the first thing is 1 times the second thing, 7 to the 4x, plus derivative of the second thing, which is 7 to the 4x times ln of 7 times 4 in this case, because that's the derivative of the exponent, and then all of that times the first thing. How can I clean this up? Well, 7 to the 4x plus 4x ln 7 times 7 to the 4x. And you often need brackets to show where your argument starts and begins of the ln part or the logarithm part, right, of whenever we're doing that. So be careful of brackets. You want to make sure that's clear. And in this case, I can factor out a 7 to the 4x. And I'm just doing this, to remind us that this is something that we can do if we have to, if we're doing something with it. Otherwise, there's nothing in the question that said I had to do that, right? But that would be the factor part. And again, ln of 7, this is something people miss, is a constant. That's a value. I can find it if I want to find it. Whoops. Ln of 7 is just some number. Okay, so keep that in mind, that it's a number. It's not something that, it's not a function that you need to take the derivative of. Okay, pi to the 5x minus 2. Well, pi is just a number. So this is a base, any other base other than e. So the derivative is going to be pi to the 5x minus 2 times ln of pi, whatever that means. Doesn't matter what that means, okay? Times, in this case, it's just 5. So again, I could rewrite that with the 5 out front, but I'm not going to bother. The only thing about this, I don't think it, once you get good at taking derivatives of exponential functions, this isn't too much harder, because the only difference is it's got that, but people forget it because we just don't do it as often. So just be mindful that it's there, and it is, and it just doesn't come up as often. So when it comes up, make sure that you remember that you got to take that constant into account. You just got to remember to write it. Otherwise, everything's basically the same. So that is derivatives of exponential functions. So cool that the derivative of e to the x is itself e to the x. It's kind of mind-blowing. Like I said, you thought trig derivatives were easy. Well, this is even easier. But we saw that once you start adding in other stuff, it does get harder. And some of the sketching for this, not going to say it's harder, but it's different. So it's actually really cool. It's kind of fun. It's really interesting. Anyway, we're going to get to that in a bit. But tomorrow we're going to do derivatives of logarithmic functions before we can move on even further. Okay, so that is it.